Hello again, and thanks for waiting till now. Today's is our webinar number 92 with the title Utilization of Tracers Application for Providing Effective FDP with our engineer Mustafa Kurtan. Engineer Mustafa is a senior reservoir engineer at Petrobel. Over to you, Engineer Mustafa, to introduce yourself and start today's webinar.
Thank you, Sama, and thank you all. First off, I would like to thank you really and appreciating your time. And truly, I do wish the product and outcome of this presentation to be valuable and beneficial for everyone from you. So I'm actually my experience with 15 years in a giant oil and gas company. And I am basically specialized in the reservoir engineering and FDP, field development planning. So our today's discussion is related to the utilization of the tracers and the importance of the tracers, and that is recently became a popular and common application, especially in the water flooding and the IOR applications in general. So we were trying to focus and highlight its importance in this kind of activities. And and since because there are many other types of the tracers that is used in the industry, like for the leak detection in the pipelines, we will not focus, and we will not review, and we will not have a discussion related to this type of tracers because it's out of our scopes of today's discussion. So we'll focus on the tracers that is served for the field development planning and for the IOR application, either water flooding or EOR applications. So let's start with our introductions. So maybe the questions now that would raise is what is a tracers and how we can use it, and we should employ the tracer, and how many types of the tracer in the market. By the end of this presentation, we are going to fulfill all these inquiries. So the tracer simply is a surveillance and a monitoring tool that is used for acquiring and obtaining the data either about reservoir of the well. And simply, we just producing the well and getting the tracer types from downhole, from in situ the wells, and get these samples, labeling it, identifying the well and the date of the tracer that was sampled, and analyzing them usually in the chromatographic analysis that is usually with DC or any other of the chromatographic techniques or the chromatographic monitoring or measurements apparatus, and then we plotting and analyzing the results of the tracers either by time or by the volume of the production. Usually it takes, both of them are the same. The cumulative volumes is a reflection of the elapsed time. So the main objectives of the tracers is, first of all, we need to understand and to evaluate and characterize the reservoir, understanding how is the connectivity and what is the reservoir is being represented, and what actually the conditions that govern the fluid movement within the porous media. And secondly, we diagnose the well performance when we're looking on the well scale itself. And in the majority of the tracer application is used for designing the EOR projects, trying to optimize the EOR applications within the field development to be more effective and optimized by introducing the tracer that shortcuts many of the experiments and the trials that we trying to employ it by using the EOR. So we are going to jump directly to the conclusion and understanding the kind of and the effect of the EOR by understanding the tracer interpretations that we will go under and we will employ it within the field. So the tracer technology types, we will start with the completion tracer, which is used just to place the tracer within the well bore. And mainly the major outcomes is clean-up verifications and also to understand the zonal contribution of each compartment and each buffer cluster. The second type of the tracer is the tracers that comes from the single well tracer, kind of is a technique called the single well tracer, which we are usually estimate the residual oil saturation. And also we have the opportunity to understand the fault and the increment in the NEOR methods. So just you can think what we will gain and what will be the reduction in the residual oil after employing or after utilizing a particular type of polymer or surfactant or a particular type of alkaline techniques. So in each method, you can able to understand what will be the reduction of residual oil. And the third type of the tracer is the interval tracer, which is used to understand the connectivity between the wells and also to know what will be the flood space and the flow channel between injector and producer, and also shape the reservoir as if there is a seismic acquisition is being carried out. So there are the major three tracer types that we are going to discuss one by one and understand the benefit and the outcomes that we can attain from each application. Additionally, understanding the circumstances and the suitable conditions that we need to suit this application to get the best effect and the best use of it. So the first type is the completion tracer. Simply, the principle of this application is there are a unique tracer type and for each cluster or for each perforation. So you simply place a completion at a particular perforations and place another tracer type that is different from the tracers in the previously inserted perforation. So you choose another different tracers and in a particular zone or in the second zone, and you choose another third tracer for the third zone or for the third perforations, and placing them with a kind of zonal isolation. So you have all to be separate. And then by the production, each production from each perforation cluster or from each zone will phase the tracer. A reaction will take place. Then it will be flowing up to the surface, combining with other productions that comes from either the other intervals or the other perforation clusters that already passed through the tracer. By this way, we are having the commingling production from all intervals and the commingling production from all the tracers. Each tracer is indicated for a unique perforation or a unique zone. So we will know how is the contribution of each zone by knowing the amount of the tracer that in the whole stream. So simply, we placed the tracer in the a completion scheme, and the production, once it flows through the tracers, you will have reactions, and that reaction will enable to dissolve some of the tracer material, leaving the main composition and the main stock of the tracers. And then by the time this tracer will decay, it takes from either 6 months up to 5 years in some applications or in some circumstances. So from 6 months to 5 years, you will be able to understand which perforation is contributing and how much is the contribution of each zone or for each cluster. So you have the freedom to either spot the tracer according to a perforation scheme or a perforation divisions, or you can do it according to the zone division. So each zone or each perforation has a unique tracer type that specify for a particular intervals. Then you measure the overall and the total production. With the total production, you can able to split which kind of the tracer are belonging to each zones, and each zones how it will be the final contribution and the final impact on the overall production of this well. So this is a simple config scheme. There's a configuration, for example, horizontal well. Mostly it's used for horizontal well, but it can be used for a vertical well, especially if you have different reservoirs or different perforations having a different characteristics, different pressures. At any case, any heterogeneous system, either horizontal or vertical, and any clustering or any multi-zones or multi-layering, you can able to employ the tracers in an effective way by just placing a different type of tracers. Here, for example, we are distinguishing them by color, but of course, in real life, just a chemical, different chemical types. And you just by understanding the compositions and the proportionality of each type, you will able to understand according to a particular hours or days scale or whatever the scale you are taking it, how many or what was the major contribution for each type of the tracers. For example, this example is just providing a clean up period, just to seeing which one is reacting or getting a clean up fluid or a clean up period for a faster time. And so this the red one representing the highest or the initial flow and the fluids that comes from the first interval, the red one. Then the blue one comes and then decaying, indicating that you already clean out all the water. The green comes first. The fourth is purple, and then the cyan comes here. The yellow one doesn't contribute in the production at all. So we understand now that is the yellow one has a problem, and this compartment or this zone or this interval, whatever, is not able to share. Of course, there must be a separation of each intervals, and then the old production will be reinforced and directly to pass through the tracer. So there is no lateral movement or intra movement between the zones. So only every zone and every cluster has to find its way only through the tracer. So it has to pass through it. It will not able to pass intra and bypass the tracer because the only inlet into the well bore is through the tracers. So once it flows through the tracer, it dissolves it and it will flow. So we analyze the concentration and seeing how the concentration is being progressed and developed over the time. For example, this type of the tracer didn't start to initiate and to contribute into the production unless we passed 14 hours. So the initial production firstly comes from these intervals. Later, these intervals contributed, but just by a shorter time. And then the green one take a little bit shorter time than the purple one. Of course, the cyan one is very late, and the yellow one doesn't contribute at all. So well, we here it's another representation. So you just seeing how is for the normalizing to see how it will be the decay and how is the rate. This is a fast rate, or indicating for the highest rate or the highest quality. The red one is less quality. So as you have a very fast decaying, it indicating a huge flux it comes in. But the time here is indicating when it started to flow and starting to interact and to respond to the drawdown that you are applying. So this one of the applications that you able to figure out what is going on downhole with your reservoir at the well point. It may have an implications or indications about the reservoir quality or reservoir pressures, but it also primarily provide you what the problem within the well itself. Why zone the yellow one it doesn't contribute? Why we have a discrepancy in the quality between each stages, and why this one is responding a very delay in indicating a lower rate corresponding to the blue one. In late time, it may provide you if something happened in the well So you will able to understand and to anticipate from where the problem happening. For example, if the well has a abrupt decline in the production rate, so you know that is those are the two primarily or the major contributing in the well. So you will able to understand and interact with the well in order to augment or enhance the productivity of those two wells. And of course, you will able to motivate the yellow one and to try to inspect why the reasons behind the non-flexibility or the non-ability to share through the well production stage. You may also have to think about not only on the well scale, on the reservoir scale, if the well has a decline or abrupt decline, why those two interval declines, either the decline in the reservoir pressure, if you're having an injection, so you have to review the efficiency of the injection in order to support those intervals. So are many indications and implications you may able to infer, I mean, or to conclude from the analysis of these types of the tracers. Actually, there are several either well scale or reservoir scales. You have to dig into your field data and to do another calibration and another measurement in order to reconcile and reshape the whole picture about the well and reservoir performance combined together. So as we were saying, many of the downhole chemical tracer aiming to detect the onset of early water breakthrough. So you are just trying to see what is the fastest one for early water breakthrough, because most of the application is just dragged or biased toward understanding from where the water is coming, but you can also having an indication about the quality or the productivity of each type of the tracer. It required a regular sampling with a fixed time. So you will able to identify the location of the water of the wells and the zone. You can make in some offshore application place a tracer not only by the zone, but maybe if you have, for example, a deep water field or a deep water case where you are running the wells at subsea completion. So in this situation, you're not able to have a surface sample to measure the water and to see how the water is being progressed over the time. So you may include each well has a different and unique type of chart tracers, and then you analyze the whole outcomes or the whole productions line. So you will get from it the tracer that belong to the well, and then you will able to understand which well is producing water and start to command the water from it. So it can be used in a different scale, either in the well scale when you need to make a segmentation within the well, or you can use it on a reservoir scale if you use a different wells. Each well has a different tracer. But the majority of the application is used for multi-segmentations within the well itself. As we said, we can just get it for cleanup efficiency. We can do it for a frag job or the simulation job effectiveness. So you see which one is being produced more than the other. You can see for the horizontal well what it will be, the horizontal segments, which one of them is the major contributors for the productions. Actually, one of the benefits of it, there is no impact on the completion design. It doesn't require the excessive or a major change in the completion design. The only thing you need to consider is to do a kind of segmentation and a kind of zonal isolation. So you are quite sure that each zone is being isolated from the underlying or overlying or from the preceding or for the subsequent intervals. If we're talking about vertical scale. So each zone is completely separate from each other. So, and the only one direction for the production is toward the tracers, or to have to quite sure that it will pass through the tracer prior to entering and being combining in the well bore and up to the surface. There is no a problem in the installation. There is less risk. The surveillance program is just taking 3 years on maximum. It may be 5 years and maybe even in 6 months. And it can monitor the cleanup efficiency, as we have said. So at that moment, it's just a couple of days. You can able to conclude the analysis and just leave the well, and you understand what it was happening during the cleanup. Also, you can able to understand how is the progress and the evolution of the water. There is no any kind of interaction with the well, so there is no kind of deployment within the well tools that may require the intermittent production. I mean, there is no interference with the well performance. Just you produce the well and then you capture the tracer from the surface, from the sampling point, regular sampling point that usually takes for measuring the water cut. So there is no any additional services is needed. And there is no production impact. I mean, there is no production defeat. It doesn't affect at all on the productions. You just analyzing and monitoring the production without as a passive measurement. Again, it's just we are repeating and trying to emphasize on what we have discussed. For example, there are different types or 4 types of the tracers that has been employed on a well, and there are each zone or each tracer belongs to each zone. So the color is being distinguished with the zones. Zone 2, for example, doesn't provide any kind of tracer, but here the tracer just designed for the water. So once there is a water production, the tracer will dissolve partially according to the amount of water is being produced. And then by the time or by the high production of the water, the tracer is being diminished and is being consumed. If there is no water production, so the tracer will left as it is, and there are no any kind of decomposition of the tracer, and in turn, there is no evidences of the tracer will be seen in the flow stream. So we have those 4 zones. For example, the green one is showing the concentration. It means there is a little bit, some kind of, might be a little water, it comes. But then here, starting, we've found it an aggressive development and in the water, indicating there is a water breakthrough issues and it become watered out. For example, the blue one here, actually, maybe also this can be considered as a kind of background noises. So you may have a very few tracer values, but since it's just moving on a very constant and very low rates, especially if the water cut is low, so you can consider it as a non-water productive. But once you see an aggressive and abrupt change in the concentration, so you can now able to conclude there is some water breakthrough, and the concentration provide you how is the proportionality and what is the majority. For example, the blue one is producing water more than the green one. If the opposite happened and the green become greater than the blue one, the concentration of the green tracer or the green zone greater or higher than the concentration of the blue one, it means that is the water comes more from the zone number 3 relative to zone number 1. So it's very simple engineering sense. So zone number 4 and zone number 2 doesn't showing any water production and the left at Z. So it improves the reservoir characterization and it enhances the production management. So you don't need to interfere and to record the BLT, especially if you have an artificial lift system, which is recording of BLT is very challenging. It's very simple, doesn't require workover intervention. Before the workover, you're able to manage and to understand what you are going to try to do. So this is a kind of tracer. Usually all the tracers types help to understand the fluid movement within the reservoir and hence help in taking the decision that affects the production strategy and the overall field development. I mean, so you will able to optimize the well intervention aerialer. You understand now what you are going to do in case of you will schedule the rig. rather than if you don't have this kind of tracer, so you are going blindly and trying to figure out and doing investigation by running the logs and having some operational impact, running applications, consuming operations, increasing the CTO emissions. Of course, that is a trendy thing. Here, for example, in this kind of application, nothing has been consumed. There is no energy here at all. Just maybe the time that you spend in computer analysis and drawing the tracers on even Excel file. It doesn't require an advanced software. It's just a very simple analysis. So, I mean, at the end, you understand what is going on downhole in the reservoir by understanding what is happening, or by analyzing just the tracer concentrations. And in case of you are considering it for a zonal isolation or for the segmentation strategy. Here are kind of real pictures about the tracer. So the tracer here is placed in this scheme, and there's a completion. So the flow is moving here down from the formation into the wellbore through this mesh, or from this perforated sub, and it finds its way and pass through the tracers, dissolving it. So there's a typical configuration of the tracers and how it's being installed and preserved within the completion string itself. It doesn't expose, so it will not damage. It just being covered, but the flow of the fluids will move through these openings, and then within the inner diameter and with the pores itself of the sub will flow and will pass through the tracer. So also this kind of this, for example, the tracer. However, we are not. There are two different chemical types, but also they are providing two different colors in order maybe easy for installation. So this kind of tracer, and this is another tracer name. So there are very small strips that dissolve within the presence of the water, and have a span life or a particular run life that according to the amount of the fluid is passing through. There are many papers and many discussions, articles. You can use them as references, talking specifically about the completion tracers. This is, for example, a real case for a frac board that you put the tracer carriers, and then we have a backers to grant zonal isolations. So the flow is being moved from the perforation and into the frac board and move upward here. So when it moves, it will pass through the tracer carrier. So we have this kind of segmentations here, as it's showing in the well profiles. So we're able to understand how it's the contribution and the volume of, or the performance of each frac board. The ones that providing higher concentration, the one is indicating or revealing that is the highest contribution and the highest quality or the highest efficiency of the fractions that is being pumped. So this, for example, a different concentration. It's like the first example, but I'm just providing you with a real example and real data. Here is the first area of the first period that was analyzed here. And this is the cumulative production over the time. So you can able to convert the cumulative production into the time by just understanding how it's the production rate. And it provides this for the cleanup period. And this showing the extended performance over among a period of the time, like, for example, a month. And then it provides you how is the contribution of each stage and how is the contribution of each stages over the time. So, for example, here you can have a snapshot or a slide, see which interval is producing more than each others, so you can order and rank them. And if you moved here, you may find in the order and the contribution has it changed Some intervals that were not contributing greatly here become here, and that is very popular in real life in unsteady state conditions. According to the pressure signals and the performances of the wells, you may have this kind of performance where the production, especially in the commingling productions, there is no steady state conditions and there is no steady contribution. The contribution is moving up and down among the intervals you are completing or are open for the production. So finally, this is like a filtered example from, so we got this data of the concentration now, and we did it here in a filtered way. So we were able to understand what it's happened. Now here, we converted it from a production into a days. So we able to see how is the performance of the tracer. So that's again and again and again is one of the basic benefit and the essential outcomes that comes from the tracers is understanding what is going on downhole conditions. So I guess now we have exposed to the tracers that is used in the completion string itself. Now we are moving on another type of the tracers that is also used in the field development and optimizing either water flooding or EOR applications. So the second type is the interwell. So when we should use interwell, and actually both interwell or the single well, the tracer that is being in single or the tracer is being among different wells are used in the same time and having the similar, they are not providing the same result, but they are providing or serving for the same objective, which is optimizing the water flooding and the EOR applications. So, but each one of them, you can generate a different result. You can employ both of them or either one of them in order to understand how is your reservoir performance and what is the fluid flow within your phase, your reservoir, especially if you are dealing with multi-phase flow. And actually, it's an intermediate step between the laboratory and the simulation EOR methods. So you will run the laboratory, and then it should be employing the tracer, then doing the design and the simulation work and the engineering work, then moving to a pilot or the full field directly. But it comes here on second time or in the second place after the laboratory analysis. So as this is a typically EOR project schedule or scheme. So you have, for example, a screening or some engineering work. Then you do some of the lab. You may have to consider the simulation by the tracer, but some people prefer to do the labs in tracers in simulation. But at any case, the tracer has to be prior to the pilot test or the full field applications. So the main benefit is we will get a quick response on how is the reaction and the impact that comes or result from employing either the water flooding or the EOR. And also we are going to risk or reduce the risk or de-risk the full field implementation. So you may employ the chemical EOR or a particular type of EOR, then you may fail. So this kind of tracer will provide you an early anticipation on what is going on in your field. And actually it's non-destructive. There is nothing harmful would happen either in the well scale or in the reservoir scale by employing or bombing or using the tracer in general. So now we are focusing on the interwell tracer. Interwell tracer is simply you are injecting the tracer from an injector well and receive with the injection into the producer well. Usually it happened in the secondary stage or in the secondary driving mechanism or secondary driving recovery. So you pump it with the water if you have water injections. Then you receive it from the producer wells, the tracer, so it finds its way with the water flood scheme and analyzing them, the same as we were discussing. So simply, we will have the tracer now is analyzing each tracer in each well, how is the amount of the tracer and the volume of the tracer happened over the time. So here, each well, you will get the tracer and the plot for well, the green one, for example, B3 or producer well 3, the concentration and over the time. So you will see which well will respond faster to the well. It's not necessary B1 or the first well that or the closer well to the injector to be the fastest well that responded to the water flood or having a quick response. Maybe the different if we are dealing with a directional permeability in isotropic system, so the highest permeability profile is moving that way rather than moving that way. So you may have the influence on B3 over B1, or maybe it follows the common sense and B1 is showing a faster one. Maybe there is some fault here, so it will take a longer time, or maybe it doesn't even respond to B1. So I mean, in each well, you analyze, so you understand by the samples, you labeled it with the well name. Now we have one single type of the tracer, so you bump it to the tracer type, and then you get in each well the produced oil and water, and taking the water itself, because since the tracer is being pumped or injected with the water, so you will take the separate water from the oil and then analyze the water. If you have the tracer is being received, so we are plotting how much is a concentration, and it usually having this profile, or may follow this profile, or maybe may follow this profile. There are different types or different profiles according to how is the connectivity and how is the flow capacity, how is the volume of the channel. Maybe this channel is big or is very small, for example. So it just can consumed or finished quickly. So you will have understand this, for example, representing a huge channel. So this well having a very big channel volume. May this well, which is the red one, has a low channel capacity. So you have a very small contribution. So now we have another thing or another indications. You will able to draw or map the structure map or sorry, the structure configuration of the reservoir itself. So understanding where is the connectivity and how much is the connections between them, how much is the volume or the bore area between producer and the injectors. It assists in understanding several and numerous implications, understanding the volumes, the volume connected, understanding the connectivity, understanding which well responded to the injector, understanding the breakthrough time. So in case of, for example, we will apply your application, we will know which well will respond first and which well will respond late according to the tracer analysis that we have generated. So in brief, the major outcomes or the results is the reservoir assessment. So we will know what kind of fault there or the channel communications. Maybe if we, in case if we found it or if we didn't found a communication at all, so there is indication there is a fault or a sealing. Also, the shape of the tracer concentration versus the time curve allow for the high permeable channel. So this showing high permeable channel and high connected bore volume respected to the black one. So each tracer configuration, because you are at the end, you analyze the area under the curve. Simple as that. So analyzing the area under the curve will provide you how is the volumes. The peak is the highest concentration indicating the permeability, the breakthrough time indicating the fastest effect. So also if there is some fault and we have found it or if we found a sum of the tracers that is passed through this fault, so indicating there is a high transmissibility. So it will help in construction or reshaping the structure map. It also evaluating the water injection and the water flooding, and also it help in the water production management. So in case of you will drill a well that at close at the vicinity of a particular well that is showing a high water breakthrough, for example, if you drill an infill well, so you have you will able to understand or to predict when will the water will reach to the producer well. For example, this is a clear example. This is a real experiment or a real trials or a real case. This is an injector well. This is a structure map. Here is a plenty of faults. If you would see, there are the producer wells that are distributing around the injector. It's a typical peripheral injection where we are injecting from the down structure. This is the dipping. So here is a contact, and that is the injector well is placing on the peripheral way, and there are the producer wells, and that is the connectivity or the streamline or the injection line from injector to producer wells. So we wanted to understand or to apply because there are a high water cut in the producer wells, especially at the vicinity of the injectors. So we wanted to apply an EOR application, and we wanted to understand when it will take a time to see the effect or the impact on the those wells. In case of we found it less than 1 year, so we will go ahead and we will proceed with this well. If it will take longer than 1 week, so we will choose another well because the criteria of on our pilot is just to check the efficiency or the effectiveness within a 1 year for a particular purpose. So the only way is to rather than we had a reservoir model and we have calculated, but we wanted something to measure it physically and precisely, so and to quantify it. So we went with bumping the tracer in the injector well and trying to detect the tracer in all the wells around these injector wells. However, there are very small faults here, but there is no fault, especially on those wells that are lying opposite to the injector and within the same block. It's very simple operation and very low cost that we used to refine, as we said, the geological and engineering model. So in case of we found something that is different than what the numerical model have provided, so we need to revisit the numerical model again, so we can either decrease or increase the transmissibility, play with some geological or petrophysical aspect in order to match the breakthrough times that attained from the tracers. For the tracer, the interwell tracer is usually bumping in a day. So in 1 day, you bump the tracer. In this example, we used 65 kilogram from the tracer, the bumping, in order to understand the performance under the water flood. And actually, you can able, according to the connectivity, the connected pool volume and the time, you can able to generate how would be with the model, the tracer of each well. So we were believing that this would be the concentration that will obtained among 1 year, just starting from the injection of the tracer. So if we injected the tracer here, that is on a scale of weeks. So we are expecting to have this breakthrough time on that well, and then the second well will have this kind of configuration according to the connected pool volume, the porosity distribution, the permeability, and all of the stuff. So we're able to produce this. Just use the 65 kilogram. That is the injector well that we connected. Here is maybe, I guess, the sample point here, but that is a sample, not the sample, sorry, that is the injection point. So this is the injection of the tracer. There are very low quantity because you are injecting it as an concentrations like a 3000 ppm among the injection line. So this injection line, for example, you are injecting 1000 barrel per day. So, and if you are in case of you just want a 2000 ppm, so just you need to inject 20 barrels of the tracers with a 2000 barrel per day. So that is the tracers, and that is the tracer pump is being placed on a trailer or it's not a skid mounted, it's a trailer mounted. So you pump it through this line and through this injection point to mix that with the injection stream into the injector well and then find its way within the reservoir and the porous media to receive to the producer. So what is the result? In fact, among nearly a whole 1 year, we didn't receive the tracer at all. So for the 4 wells that we pumped, we didn't receive any tracer at all for the producer wells. So indicating, however, we have an indication and we know from the salinity, because we are injecting at different salinities than the formation salinity, there is a communication, but the communication will take a longer time than it has thought. So which means that there is some complications, and the injection pathway is being moving in a complicated way than we thought. So we adapted and we modified our geological perception about this field. And of course, we discarded this injector well from applying this particular EOR application, and we choose another well that showed a faster or a quicker time, or the effect was in a quicker time. So that actually is the well that we considered it for or we used, or this is a case that where we used it because it showed a very quick response and a very fast effect with the injected water. For example, this is a production well. That is a water cut, the blue one, and this is a salinity. Actually, the produced salinity is a combination between the formation salinity is at nearly 200,000 ppm, and the injected water is 40,000 ppm. Basically, it's the seawater injection. So this salinity is a mixture between the formation and the seawater. So as long as the salinity is going down, it means there is a dilution and more seawater. As the salinity is moving upward or higher, it means a more formation water. The salinity itself may also exist as a tracer. In fact, by definition, it's just indicating how is the dilution. So by the concentration of the salinity, you may be able to understand how much the seawater or the injected water now is being received into the producer well. But you cannot quantify it precisely as the tracer does. So, for example, in this well, we here started the injection. The pressure was 800 psi or 900, almost 900 psi. After like 6-7 months, the pressure has increased up to 4,000 because there are a very low or a very confined channel. The same has been indicating here by the higher water or the water breakthrough that nearly happened within 6-7 months. The salinity also become diluted, so it has decreased noticeably, and the water cut has progressed with the injections. In this period where it was highlighted or noted by stop injection, there is a stopping in the injection occur for any reason we ignore. For example, a problem in the injector well or in the plant or whatever what happened. Now we have a problem in the reservoir pressure that has declined because there is a lack of the energy. It has impacted on the production rate or the growth rate. Also, the water cut has decreased accordingly, and the salinity may show some increased in its values. We resumed the injection here. So what we resumed after a while, it has increased back again. The growth rate also, we found it, or we enabled when we went a work over to upgrade the pump in order to accommodate the higher pressure and utilize the high pressure that we increased. Also, the water cut has increased. The same has been repeated. When we stopped the injection at the period, the pressure declined, the water cut a little bit declined, the salinity has increased a little bit. And then when we resumed the injection, the pressure returned back again, the water cut has increased again. So, I mean, after a small period or a small time scale, we had the indications that the injection does matter in this well, and the effect is strictly obvious. But how much exactly, that's what we wanted to quantify by using the tracer. So now we prove the connectivity, and we know that when we just have a focus, when we started the injection from the middle of 2002, the injection had started here, accompanied with the decline in the salinity, indicating that we have a dilution and the seawater effect or the injected water that arrived to the well. nearly it has 6 months. When we applied the tracer in this particular well, it has indicating and revealing the same values, and a decent match has obtained between the salinity and water cut, and even the pressure that is usually increased and observed within 6 7 months. So we have increased in or the water breakthrough within 200 days. We recorded also a BLT. We found a high perm streak, different than that other intervals that is injected, that is a sand, the whole perforated interval. Only injection or the injection only goes for the upper interval, like 20% or 10%, and the other 90% nearly doesn't receive anything. So now everything is well knowing and quantified, and now we are quite confident about the effects that would appear within a shorter time or within less year. And we have confirmed the safe zones, and also the tracer campaign assessed precisely the breakthrough time. There are the case that we were discussing, that is injector well and the producer well. We have about 260 meters. So we were proving a candidate selections. So we had to choose the proper candidate selection. We did a new data acquisition like BLT and the tracer. Then we designed it. So we calculated according to the tracer considerations that we have provided, how much is connected pool volumes and the slug that we used at 220 barrels. We employed the micropolymer, which micropolymer is a kind of a polymer that is being pumped as a liquid phase with very low viscosity, or viscosity nearly closer to the water. And at it progressed within the reservoir temperature is being higher because we are injecting in a colder environment since it's injections. Once it moves within the reservoir, toward the producer, the temperature is going higher. Once it at a particular time or a particular temperature, it is starting to consolidate and is increasing the viscosity 1,000 times. So it clock within the middle point between injector and the producer well. So you will able to divert the injections toward laterally and vertically. So at that moment, you're able to enhance the sweep efficiency towards the producer well. It's completely different than the normal, ordinary polymer flooding, where you are just pumping the polymer as a slack and move its way and it sweep all the way from injector to producers. But now it's just a kind of intermediate plugging within the reservoir itself or the porous media, and then doing lateral and vertical diversions within the reservoir. So we bumped the treatment, and as expected, a decrease in the water cut and increase the oil rate. Also, we increased the water salinity as an indication on the a new fresh or a new flush of water that was moved towards the producer well. So it indicating a new busway has been created or displaced. So at the end, this kind of interwell tracer test helped us to understand what was or helped us to rank the candidate or to choose the best candidate among the others. It helped us to understand, to give a better understanding and the perceptions of the reservoir, the connectivity, the pool volumes, the fault, anyway, it's just shaping and constructing what is intra between the wells. That's why it's called inter-well inter-tracer test or inter-well tracer test. Now we are moving to the third type, or the last type is the single well tracer test. The third well is just as from its name by definition, it's just used for only one well. So it doesn't require to inject in a well and receive the tracer from another well. No, just you inject in the well and getting the production from the same well. It's simply, or the main purpose of it, to measure or to attain the residual oil within the reservoir. So we need to understand what is the current oil residual now. You are usually produce the well, and there is a water cut is being moved. So there is some a particular saturation here. So rather than moving the cased whole log, which provide you a very short distance around the producer well or on the well, just a few inches or maybe a sub feet. So it will provide you a bigger area on how is the data or how is the performances of the well within, or how is the residual oil within the reservoir around the well will. So it provides you a deeper investigation on the residual oil rather than the logs that provide you a very slow or a very short, or I would say, I can describe it with as in-depth investigation is very low compared with that one. So provide you a higher certainty. Maybe also the log is being masked by the cooning, so it will provide you the wrong or mistaken information. So now you understand how is the residual oil within a few feet, maybe several feet within the reservoir. And how it happened, just you are after producing the oil and water, and now we are having a particular oil and water saturation. What we do now, we do the opposite. We inject a water, either formation water or seawater or the injected water itself. So you have the freedom to choose. For example, if you do a formation water, so you get the residual oil. If you will get the seawater, so you will see, or the injected water that is used for the injection, so you will get the residual oil after the water flooding. So whatever the type of the water you inject, so you inject the water, and now after a particular time, for example, 5 or 6 days, so the slug will move, for example, to this toward or till reach to that depth. You bump the tracer, a slug of tracer that continue also or last for 3, 4 days, 5 days, 6 days, according to the design, a particular time. So the water, the initial water will move to reach to here, and then the tracer will move to that depth and flush it with the displacing it in order to place it in deeper to the reservoir. So the tracer now is being placed. This is the injection way. This kind of chemical tracer, in fact, there are 2 types of tracer. But simply, the concept is the organic tracer types, like ester. When it's being pumped, it is being, the chemical reaction is taking place. So it is being hydrolyzed and the partitioning. One of the partitioning of the tracer is moved toward or react with the water, and some react with the oil. So the green one is representing to the residual oil, and this one is representing to the water. So one will react with the water, and one will react with the oil. Then the shut-in time that you allow it for the reaction and the partitioning. So that is the initial form. Now it becomes 2 types of tracer. The tracer is being dissolved or resolved into 2 types. Type attached with water, and type like partitioning in the oil or attached to the oil. Then when after a particular time of shut-in equal to the same time of injection, will produce with the same equal time of the production in order to preserve the consistency of the measurement. So when we produced, mainly what it will produce the first is that water that comes from the tracer that is partitioned in the water. And there will be the tracer that the oil will be held for a little time before it moving the upward to the with the stream of the production. So again, this is another illustration. We have here injecting the water, this kind of tracer or ester tracer. So this ester, the red one is the tracer, is being injected with, that is a pre-flush stage, which is, for example, seawater or formation water. This is the stage of the tracer, and this is the stage of the post-flush. So we inject, then we shut in a particular time. So the tracer now is being dissolved into 2 times or hydrolyzed into 2 types. The first type is attached to the oil, and the second one attached to the water. The one that is, when it's the ester connect or reacted with the water, it produced acetate and produced alcohols. As you know, the alcohols is being attached with the water, like methanol, ethanol, whatever the type of alcohols. So the alcohols will flow with the water. When we produce the bag, the blue one will move, and the red one will leave with the oil stream, and then it moves later on. What it will happen later, we analyzing the concentration during the production. So from this well, we take the samples from the production stage, and we analyzing the concentrations of each type of tracers according to the volume produced. And the volume produced is nearly equivalent to the time. So they are both the same. So, and we are drawing the concentration. Ideally, it should be like a very narrow space here and a very narrow space here, but according to the conditions of because you are not moving in like a piston like, so may the higher concentrations will having or will follow a normal distributions. So it will not have, so there's a kind of dispersion will take place. So we will have this kind of configuration. May have the blue one is larger than the red one, may have the blue one or the alcohols that comes with the water is very far from the red one, but at any case, the alcohols comes first, then the ester that belong to the oil. So you have to understand or to expect that the alcohol's concentration come prior to the ester that comes from the or that attached to the oil. Then with this equation, so you have to choose the peak of this peak and identify this peak. So this represents the Q of alcohols, and this represents the Q of the esters of the oil. And doing this, identify the beta value. So the beta value is very simple substitutions. It's a kind of a proportional ratio. You substitute it here, and K is giving for a particular tracer type. It's a lab measurement that understanding the partitioning. How much when we inject this water into this kind of salinity, how much the oil it will split into oil and water. So you measure it at the lab and substitute it here, and the beta comes from this measurement, those three factors, and those two factors, the ester and the alcohols, comes from the peak of the produced tracer Z. A very simple substitutions, then it can produce the residual oil. So it comprises, as we will explain or letters, a sequential of analysis or a sequential of steps: injection, shut-in, production, injection, shut-in, production, and so on. So here, about a real example or a real case where we try to employ or to measure the residual oil saturation. And also we wanted it to investigate the potentiality of the low salinity water flood and see what is its beneficial effect. So we managed to do it through the two injection fluid types. We injected seawater, then we injected the low salinity, and see how is the differences between the low salinity and the seawater on the residual oil saturation, and whether the low salinity providing the residual oil over the seawater or not. It took actually at that moment about 1 month. So it depends on how is the volume, but roughly speaking, or the typical period is from 3 weeks, maybe up to maximum 2 months. This kind of measurements. A rigless operation, by the way, doesn't require the rig. So here there were a 2 cycle. We wanted to investigate. First, we injected seawater with 500 barrels per day. Then we shut in for a particular time, and we try to produce with the same injection time. So there is a production comes from ESB at that moment. So maybe it's not a pretty constant, but just we tried as much as we can to make it closer to the injection rate. So we analyzing the production period. Then from here, from this analysis, we understanding how much the residual oil that comes from the seawater. Then we tried by injection of low salinity with the same well. So we flood again with the low salinity. Then we shut in and we produced the well again around 500 barrels per day. And then we identified the residual oil from the analysis of the tracers, as we explained from the two peaks. In case if we found that the residual oil that comes from Lucerne is providing or a less or a reduction in the residual oil over the seawater, and indicating that is the low salinity or the low sal injection can provide a more sweep displacement efficiency and microscopic efficiency, and it can develop and displace more oil than the seawater. You can do it with a surfactant, but you have to consider, this is a very important note, to move with the scheme or the type of the trace of the application that provide the highest residual oil, then followed it with the lowest and the lowest, and so on. I mean, you cannot start with the low sal and then move the seawater, because it's knowing that the low sal can provide, maybe can provide a reduction in the residual oil over the seawater. So in case of you do it with the low salinity, so of course the seawater will show no change in the residual oil, but you cannot rely on the data of the seawater. The same for the surfactant. You can apply the seawater, the low salinity, maybe surfactant, maybe later a nanotechnology. So you can ordering it on a ascending way. You cannot start with the ones that provide a reduction or a great reduction in the residual oil, then you move with the one that provide a less residual oil reduction, of course, because you will not conclude an appropriate result. So it will be misleading. So start with the one that provide a less efficiency, then moving with a higher efficiency, then you move with a greater efficiency. You can repeat it 3 or 4 times according to what's the kind of, if you need to rank a different type of the EOR application, so you rank them, which one provide a less residual oil, and then you can plot them. And you have the freedom either to start your field on that sequence, or you go directly with the ones that provide the lowest residual oil. So we were injecting it with 40,000 ppm salinity seawater, as we were explaining, that is the seawater. And the low salinity water, it was that moment was 1,000 ppm. Then the injection and production rate was 500. It take nearly whole August, so 1 month, with this sequence. That the actual curves that we obtained. So that one, that is a concentration of the ones that partitioning toward the water, and that is the one that partitioning to the red one is the water, the alcohols, and the one with the ester. Of course, there's a peak here that you can consider here is a peak, is completely different than that peak. So we tried it on 2 wells, in fact. So one will take 1 month and one will take 1 month. And then in order to quite sure that we have a consistency on the data. And actually the seawater provide a constant values. So this is the one with the seawater and that one with low salinity. So of course with the seawater, if you would see, we have here, that is a seawater effect. So you subtract the biggest or the values from the peak or the highest value of the concentration and the highest value of the concentration, that is the seawater. And you do the same here for the low, from the low salinity. If you would notice that is the 2 peaks become closer, indicating the difference is low, indicating we have a less residual oil. At the end, the seawater provided residual oil 18. The low salinity provided a residual oil 14, that for a well. So we did the same analysis in another well, and we provided it with these ranges. So we will saying if you consider it the reduction in the residual oil from 5 to 9%. So it means that there is a potential of low salinity on this field. If you reduced the whole reservoir by 9%, the residual oil saturation, imagine how it will be the recovery in case of you populate it in the whole field. And of course, it's a function or depending on the reservoir volumes. So this is the technology. Maybe someone would choose the low, the another type of tracer, so you can choose another type. So as we were saying here, that is the seawater provide 23 of the low salinity. The seawater, the low salinity, one well provided 18 and one well provided 14. So we have this kind of reduction. So as we were saying, it may you apply the surfactant can provide 14. So it means that the surfactant doesn't provide any reduction in the residual oil. So you have to choose either low salinity or surfactant. Of course, the low sal is much cheaper. May be the surfactant will provide like 5 as the residual oil maybe go down to 5 might be. So at that moment, it will provide an incremental and greater reduction in residual oil, so will be highly potential. So that is the sequences of the single well tracer test. You pump and you shut in, and then you produced, you analyze by these equations. So with these equations, the two streams or the two peaks, the one with alcohols that is dragged or attached with the water or hydrolyzed with the water or partitioning with the water, and the one with the esters that is partitioning in the oil, see the differences between them with the peaks, and very simple substitution, you get the residual oil, you repeat it with a highest efficiency treatment, surfactant, lucelle, whatever you can moving, as we're saying, in ascending way, but not descending way. So you will able to figure out and to rank the effect of the residual oil. So in case of, for example, the seawater provides the same of the low salinity providing the same. So at that moment, you can conclude that is the microscopic efficiency will not changes greatly with the chemical EOR, with the EOR application. So you will understand and you save the time for the pilot test and the money for the pilot test. Personally, I would prefer to do the single well tracer test even before conducting the simulation model. In case of practically concluded, so you will save the time for exerting an engineering effort for trying to mimic the reservoir performances and doing an extensive reservoir analysis. Here is a conclusion. Our, like saying, the conclusive message is tracer study is crucial for any OR project and maybe for any, or generic for any field development planning. We have reviewed the 3 types of the tracers, the compilation tracer, where there are several tracer material per a single producer well. And we have learned what we called, or what is being called by interwell tracer, and we know why it's called interwell, because it's seeing and shaping between the wells. There are several single tracers material for many or maybe a single injector well. You may consider in this a different injector well, and each injector well at that moment will have a specific tracers. So you'll see if you need to increase the complications and the complexity of your analysis. So if you have different injectors, so you can have a different connectivity of the producer between or among those injector wells. Also, you have the third one is a single well tracer test, which is a single material that is used for a single producer well. So at the end, we're able to finally understand the knowings and the unknowing. So there's many things that is we believed it's knowing, but actually is unknowing, and the opposite is true. So thank you so much, and now it's yours, Asim, for managing the webinar.
Thank you so much, Engineer Mustafa, for this amazing webinar. Now time for questions. If anyone have question, please type it in the chat, and we will read it to Engineer Mustafa to answer. So there's a question from Yasin. I'm not sure the question is clear enough, but I guess he's asking which tracer is used in injection, if I got the question correctly.
So he mean I don't know if he is asking about because which type of the tracers. Yani, for example, all of them are a chemical tracer. You may use a radioactive tracer, which is now become less popular due to the environmental impact and the health. So for the HEC now is restricting for employing or relying on the radioactive tracer. So majority is relying on the chemical tracers. So 95% of the tracers are chemicals.
Great. Any more questions, please? I believe we have exceeded the time for this webinar, but we can still have a few minutes for receiving questions. So if you have any question, please get the opportunity to ask now. Great. So seems no more question. So guys, if you would like to review this webinar, you know it's live on YouTube, so it will be recorded just after we finish this live. So you can revisit it and many other like more than 90 webinars available on the YouTube channel. So feel free to review any of them, increase your knowledge, and boost your potential. Thank you. Thanks to Engineer Mustafa. Have a nice night.